Right, section 5.4, pretty much the halfway point through this chapter. In this, we're going to learn how to multiply and divide radicals. We're possibly going to be using again some of those skills that we learned in 5.3 when we learned how to add and subtract. We're definitely going to be using simplify skills, as you can see right here when we talk about adding or multiplying radicals, because in the end, after we do multiplying, you're going to simplify. Now, when I talk about multiplying, I always had this saying: numbers will multiply numbers and radicals will multiply radicals. So unlike what we dealt with in 5.3, where in order to add and subtract, you had to have like radicals to put them together, and this one, it doesn't matter. So the numbers in front of the radicals will multiply each other, and the numbers underneath the radicals will multiply each other. That's what I'm saying here. Numbers multiply numbers, radicals will multiply radicals. So let's take a look at some examples here. So if you want, go ahead, pause the video, give this a shot. It's just two radicals, multiply them together, and then simplify. Okay, so when you multiply these together, you get the square root of 16, because 2 times 8 is 16. Square root stays, okay, because they're not the same radicals. And what is the square root of 16? Well, that's one of those perfect squares we know. So the answer is 4. There you go. See, radicals multiplying radicals. So go ahead, pause it, give this one a shot. Okay, so when we multiply these two, because again, they're both radicals, you get the square root of 18. Now, this is not a perfect square, so we use those skills again that we learned in 5.1, and we break this down. And as I told you in 5.1, I'm always going to use good child, bad child from here on out. So the biggest perfect square that divides this is 9. And what times 9 gives me 18? 2. The perfect square is our good child, so it gets to go out, so that's 3. Square root of 2 stays indoors. And there is the multiplied answer for the square root of 3 times the square root of 6. It's 3 square roots of 2. Okay? Again, you're just using the same techniques that we had from 5.1 after we do the multiplying. That's all you're going to do. And again, radicals are multiplying radicals. They don't have to be like radicals. All right, go ahead, pause the video, give this one a shot. Okay, so off the top of my head, I do not know what all that is. So it's 2 times 16 times 4. So that's 128. So we have the cube root of 128. Because again, all we're going to do is just multiply all the way across. Okay? So now, I don't know if that was a perfect cube or not. I don't have that list memorized. I got the perfect squares memorized, but not perfect cubes. So we just go to math. I'm going to choose number 4 since it's a cube root. Actually, no, I'm going to choose number 5 because I always like to reiterate that one. It's a cube root, and we got 128 underneath. Oh, so it doesn't work out. So now we do have to see if this thing can reduce down by using perfect cubes. Okay? Well, the first perfect cube we have is 8. Oh, that works. So that's good news. The next perfect cube you have is 27, because that's 3 times 3 times 3. Let's try that one real quick. Nope, 27. So far still, the biggest perfect cube we got is 8. 128 divided by, the next one is 4, and I believe that's 64 is the perfect cube for that one. Oh, 64 is now my biggest perfect cube that divides it. And I don't do I could do the next one. The next one is 125. So 128 divided by 125. Nope. So the biggest perfect cube that divides it was 64. So we've got the cube root of 64. And that is times 2. What is the cube root of 64? That comes out nice and neat to be the number 4. And that's the cube root of 2. It stays. And there you go. All right. Go ahead and, well, let's talk through this one. So again, just kind of going back to what we just talked about, my beginning mantra is numbers multiply numbers, radicals multiply radicals. So this 2 and this 3, those are what I consider the numbers. They are out front of the radical. So the 2 and the 3 will actually multiply each other and give us 6. And then, of course, the square root of x and the square root of 2x, those are radicals. Those will multiply together, and that will give us the square root of 2x squared. Okay? And just like you learned in 5.1, we're going to break this down into its separate pieces and then put it all back together. So we know that we have a 6 in front. Let me change up the color. We know that we got a 6 in front of our answer, but this guy breaks down to a square root of 2 and a square root of x squared. There's nothing that we can do with that square root of 2, so that stays the way it is. This is a bad child. It's not a perfect square, so there's no breaking that down. It's just got to stay. Now over here, the square root and the square actually take each other out, because remember that from 5.1. So we have an x that escapes there. So when we put all this information together, we know that we got that 6 in front. We also got an x that is in front now. And then this is what's left inside. And that is the final answer. Again, we're taking the techniques of multiplying, and then all we did was apply the techniques that we learned in 5.1 right there. All right, go ahead and give this one a shot. Go ahead, pause, and go. Okay, so when you look at this one, we need to distribute this through. So hopefully you were thinking that. Now, we are taking the square root of 7 and the 2, and we needed to distribute this to that. If I take and distribute it through, I'm sure some of you probably gave me the answer of the square root of 14. But that's not true. That's not what's going on here. Because remember, this is a radical. This is a number. Do they multiply each other? No. But I still have to write them both down because the square root of 7 got distributed to it. Okay? So even though these don't multiply each other, you still write them both down because it's coming there. And then these two are definitely radicals, so they'll multiply each other, and that will give us the square root of 21. So the last thing you got to do is look at these. Does this radical break down? Square root of 7? Nope. Does the radical square root of 21 break down? Nope. And then since we have addition going on, again, this is what I said, we might have to apply some of that 5.3. Can these two radicals get together? No, because these are not like terms, just like what we talked about in 5.3. So that actually is the final answer there. See, not too crazy. All right, go ahead and give this one a shot. Multiply and then break it down. Okay. So the square root of 5 can definitely multiply that square root of 10. So that's going to give us the square root of 50. And the square root of 5 will definitely multiply that square root of 8 and give us the square root of 40. Okay? Can these break down? Absolutely. The biggest perfect square that divides 50 is 25. The bad child is 2. Square root of 25 is 5. Square root of 2 stays. Over here, the biggest perfect square that breaks down 40 is 4. And then you have the square root of 10. This is the biggest perfect square that divides it. So what's the square root of 4? That's 2. Square root of 10 stays because that's the bad child. And we got a plus between here. Now the last thing is, since we've broken everything down, can these two radicals combine together? No, because they're not the same. This is the square root of 2. This is the square root of 10. So that is the final answer. Again, you can only add and subtract radicals if they are the same radical in the end. Okay. Go ahead and give this one a shot. All right. So in this one, if you were thinking FOIL, you've got it. All we got to do is FOIL through. First, outer, inner, last. Okay? So we're going to take the 1 and multiply it by the square root of 5. Can they really multiply each other? No. but they don't disappear, so we still have it. So 1 square roots of 5. Okay? Then we're going to take the outer. So 1 times negative 4, that'll work because numbers multiply numbers. So 1 times negative 4 is negative 4. Then we'll take the inner, and these two can multiply each other because radicals multiply radicals. That gives us plus the square root of 35. And then the last. Again, this is a radical. That's a number. They do not multiply each other, but they do not go away, so we have to write them both down. Last but not least, is there any reducing of the radicals? Well, square root of 5, that has to stay because there's nothing that can reduce it. Square root of 35, there is no perfect square that divides it. Okay. Square root of 7, that stays as well because there's no perfect square that divides it. Is anybody getting together? Well, no, because none of the square roots can get together. They're not the same, and I don't have any other number to get together with that. So this is actually technically the answer. 1 square roots of 5 minus 4 plus the square root of 35 minus 4 square roots of 7. Yeah, because there's no reducing and there's no radicals adding or subtracting together. So it stays the way it is. Sometimes that's how it works. All right, so go ahead and give this one a shot. Pause the video. Get after it. I believe this is the last multiplication. Then we talk about division. Yep. So go ahead, pause, and give this a shot. All right. So remember, back in 5-1, that if we take two of the same radicals and multiply them together, and again, they have to be exactly the same, what happens is what is underneath pops out. This is a very important property that we're going to use a lot in this section of 5.4. So if the two radicals we're multiplying are the same, the number pops out in the bottom. Whatever's underneath pops out. So these two radicals are the same. So what's underneath is going to pop out. So square root of x minus 2 times square root of x minus 2 is x minus 2. Radical's gone. Okay? So now we do outer. So I've got a square root times a number. Do they really multiply each other? No. But you don't make them disappear. You have to write them both down. So you got negative 3 square roots of x minus 2. Okay? Then in here, we're going to multiply the inner. Again, it's a number times a radical. So that'll be a positive 3 square roots of x minus 2. And then we have last. 3 times negative 3, we can do that. That's negative 9. So is there any reducing of the radicals in here? No, there's no way that we can reduce these. But we can add them together. What's going to happen with a negative 3 square roots of x minus 2 and a positive 3 square roots of x minus 2? They're going to cancel each other out because negative 3 plus 3 is 0, and that cancels all of that out. So this piece is now all gone. They just canceled each other out. All we do now is combine anybody else. Well, that negative 2 and this negative 9 can get together. And so that will give us a negative 11. And then that x, it's going to stay the way it is. No one gets together with it. So your final answer is x minus 11. Or negative 11 plus x. It's all the same. Because this middle term right there canceled out. Okay? All right, let's talk division. Let's talk division. So division, there's a little bit more. And with division, these first 3 steps here, this is actually kind of like a large step 1. And I would try them in these order. First, I would take, numbers divide numbers, radicals divide radicals. Okay, just like in multiplication. I would try and see if I could do division. If I can't do division, then let's see if there's any perfect squares that we can take care of. Okay? Because if there are perfect squares that we can take care of, that makes life a whole heck of a lot easier. If there aren't any perfect squares, then the big thing that's in here that we're going to talk about is what we call this rationalizing. Okay? So that's the big thing with division that we need to make sure that we understand is how to rationalize. Okay? All right. So these first 3 steps, you're not really doing all 3 of them. Really, like one of them is going to be kind of like your guiding principle. And after you take care of the division part, which is what these first 3 steps are, then you go into simplify mode, where we'll take care of the radical and then we'll take care of the numbers. And you'll see that come up here in a second. Okay? So that is the idea behind division. So I've got some examples. Let's start talking about these. So right here, the first thing I want to try is, can they actually divide each other? No. But remember back in 5.1, we had that property that says if I have numbers under, or if I have a fraction under a radical, remember that we can separate them, right? Yes. Good. I'm glad you remember that. So if I separate them, look at what we've got. Square root of 16 over the square root of 25. And hopefully you recognize those as perfect squares from the very beginning anyway. So this is one of those where we're not dividing, we don't have to rationalize. What we're going to do is we're going to take care of perfect squares. Okay? So what's the square root of 16? That's 4. What's the square root of 25? That's 5. And there's the answer. Just like what we did back in 5.1. All right? So taking a look at this, well, obviously these are not perfect squares. The square root of 72 is not on my list. The square root of 2 was not on my perfect squares list. So we're not doing perfect squares. But remember this property that I just said right here? This property works forwards and backwards, so you know. So sometimes, if I could just get the 72 over the 2, can't 72 be divided by 2? Absolutely. So in this case, this is where I want to take that property we just had right here, where they're separated, and I want to put them back together because I want to perform division, because I can have radicals dividing radicals. Okay? So I can put them back together and put 72 over 2, which 72 divided by 2 is 36. So this becomes now the square root of 36. And that's much easier to deal with, because we know what the square root of 36 is. It is 6. And that's the answer. Okay? So you see how what I'm talking about with my rules back here. Sometimes you might want to divide them. Sometimes you might want to take care of those perfect squares. We'll get to rationalizing soon. Okay. So on this one, go ahead, pause the video, give it a shot. Okay, hopefully you recognize this as perfect cubes. And again, we can separate these. So you can have the cube root of 8 all over the cube root of 125. And perfect cubes, we can take the cube root of those. Cube root of 8 is 2. Cube root of 125 is 5. Yeah, just like that fraction problem that we did with the 16 and the 25. Except there was a cube root this time. There you go. All right, jumping over here to the next one. So in this one, go ahead, pause the video, give it a shot. Okay, so this one is just like what we did with the one where we had the square root of 72 and this over the square root of 2. Put this stuff back together. Okay? So 45 x to the 5th all over 5. And 45 can be divided by 5. So that will give us 9x to the 5th. See, numbers are reducing each other. And this is much easier to deal with because we know how to simplify this radical. We'll just separate it out. 9 and x to the 5th. Okay? Well, we know what the square root of 9 is. It's 3. Square root of x to the 5th. Well, remember we can go back to what we did in 5.1. Write all your x's. It's a square root, so you're circling pairs. So 2 pairs of x escaped. This pair did not escape the jail. And that actually is your answer right there. If you want to kind of clean it up and put them closer together, that would be fine. So that is the answer. Okay? So right there, you saw the last step where once we did the division piece, we had to simplify things down. Okay? All right. Now let's talk about this one. Because this is where, I mean, granted, we know what the square root of 81 is, and we can take care of that. So we can take care of that square root in the top. If you tried to put these back together, 81 divided by 11 does not work. 81 divided by 11. See, doesn't work. So this is the rationalizing problem. So let's talk about the square root of 81. We know what that is. That's 9. And what we have is the square root of 11. Now, with this, some Joe Schmo mathematician long ago said, we need to learn how to rationalize because I don't like radicals in the denominator. And that's the problem here. As mathematicians, some Joe Schmo long ago said, I don't like radicals in the denominator. We're going to rationalize it. Okay? And the only reason, this is the only thing I can find, the only reason he didn't like radicals in the denominator is because this was an irrational number. That's it. Because this thing was a non-terminating, non-repeating decimal, we can't have that in the denominator. So we have to now learn how to rationalize. Rationalizing is super easy. Whatever radical is here in the denominator, we're going to multiply the top and the bottom by it. So we're going to multiply by the square root of 11, square root of 11. Okay? And the reason we multiply by that same radical, because we talked about this. What happens when I multiply two radicals that are the same? The number pops out. Square root of 11 times the square root of 11 is 11. Okay? Now in the numerator, what do we got? Well, we've got 9 times the square root of 11. But because this is a number and this is a radical, they don't like each other, but they don't disappear. So in the numerator, you have 9 square root of 11. And then this is where that last step of simplifying we got to look at. So we look at our radical here, square root of 11. Can that break down any? No, there's no perfect square that divides the square root of 11. Then we look at our numbers in front. 9 over 11. Can that fraction reduce? And no, it cannot. So that's what I mean in the end by reduce your radical or simplify your radical and then simplify your numbers. Okay? In this case, this radical did not simplify and my numbers did not simplify, so that's the answer. All right, this is the last problem. So again, when you look at this, there aren't any perfect squares to take care of. We can't do any division between the top and the bottom. So we have to rationalize. So we have a radical down here. Now, many of you are probably thinking, Mr. Armstrong, let's just multiply by the square root of 3. And I would be like, that's cool because you learned what rationalizing means. But that's not gonna take care of what we have down here. Because if I multiply by this square root of 3, if I distribute that through, I end up with 7 square roots of 3 minus 3. You see, I still have a radical down there. So multiplying by the square root of 3 isn't enough. So this is where I got to teach you one last concept for 5-4, and it's called a conjugate. Whenever you have addition and subtraction in the denominator and you have to rationalize, you have to use what we call conjugates. Okay? So a conjugate is, and this is like in the bottom, so like if I have an A plus a B, say that's my bottom, and say that the A is like 7 and the B is the square root of 3. In order to get rid of this 7 plus the square root of 3, pretending that this is, I would use the conjugate. And the conjugate is just turn the addition sign into a subtraction. That's all a conjugate is. Take the statement that's in the denominator, change the addition to subtraction. If it was subtraction, you would change the subtraction to addition. That's a conjugate. And that's what we have to use on this problem. And you're going to see conjugates pop up again in 5.6. I guarantee it. So if I come back to this problem, I got 7 minus the square root of 3. So in order to rationalize this, I need to use 7 plus the square root of 3. And that will get rid of the radical in the denominator. Okay? So now what's going to happen is in the denominator, you want to use FOIL. But I'm going to teach you a faster way to get through this. We don't really have to do the full FOIL on this. The reason why we multiply by the conjugate is because this gets rid of, if we did FOIL, multiplying by the conjugate takes out the middle term. These two, if you FOILed out, would actually end up canceling out. So technically, all we have to do is what I call the Florida. When you multiply by conjugates in the denominator, all you really have to do is multiply the first and multiply the last. I call it the Florida. Okay? So if I take 7 times 7, that gives me 49. If I take a negative square root of 3 times a positive square root of 3, that gives me a negative 3, because a negative times a positive is negative, and they're the same radical, so the number pops out. So in the denominator, we have 46, because 49 minus 3 is 46. So that is a rationalized denominator. And then on top, all you would do is, in this case, just distribute, although sometimes you might have to FOIL on the top depending on what's there. So what's 1 times 7? That's 7. 1 times the square root of 3 is still going to be the square root of 3. Or if you want to put the 1 in front, you can do that. So this is the numerator. Last but not least, is there any, can I reduce that radical there? No. Can I do anything about my numbers on the outside? No, because again, this is a family, so I can't just reduce the 7 over the 46. It doesn't work like that. And that is the answer. And that is section 5.4. Have fun, ladies and germs.